All right, let's do some examples of differentials. We're going to use the formula established in the previous video, dy equals y prime times dx. So this is where dy and dx are representing change in y and change in x, not for the function, but for its linearization. Okay? So applying that formula, if we have y equals x squared plus 5x, well then dy is going to equal the derivative of this, which I can take here real quick. That's going to be 2x plus 5, all of that multiplied by dx. There we go. That's as easy as it is. You just take y prime and then put a times dx on the end. And that's what dy is. So what this is now telling us dy is like an approximate change in y. Okay, remember dy is like approximately delta y, right? We're using the change in linearization to approximate the change in function value. So change in y is approximately going to be equal to this, which is a function of two things. We basically have two independent variables here. We have the x and we have the dx. So this the change in y depends on what x you calculate the slope at. So where do you calculate your tangent line? And then also how far away from that point where you calculated the tangent line are you trying to look, right? How far away is your other x point? So it's like if I've got my curve here, then I pick first of all I pick where is x, right? Then you get a tangent line, and then you say, well, the change in y is like how much you're going to go up and down, and so my other point is going to be somewhere else, a distance dx away, and then the change, would be approximated by this amount, dy, which in this case, in my picture, is drastically different from the actual change, which would be that amount, delta y. So I know it's kind of a bad picture because they're not actually close to each other, but that's the idea, all right? So it depends on these two things. Where do you start? So where do you start and how much do you change by? Okay. So let's just do a couple other ones. If you have y equals e to the x, then your dy is just going to be the derivative of that, e to the x times dx. That's nice and easy. If you have y equals sine of x, then your dy is going to be cosine of x times dx. You'll notice if you divide by dx, you get, you just get the statement, dx here. If you divide by dx, the dx's cancel out, and you get the statement dy over dx equals the derivative, which is basically, this is sort of like backwards justifying the Leibniz notation. Okay, Leibniz notation is a fraction because it's literally rise divided by run, and this is rise over run for the tangent line, which is therefore equal to the slope of the tangent line, which is the derivative. So this all kind of feels like we're maybe approaching it backwards, like we already learned about derivatives, and now we're relating that to the slope, and now we're relating that to rise and run. Which felt like maybe where we should have started the conversation, but I think that despite feeling like approaching it kind of backwards, having already learned about derivatives and got a bunch of results about derivatives, we are now able to use this idea of rise over run to then do approximations of change for different functions. Okay, we're approximating the change in value, change in output for different functions. So we're going to now go ahead and take this, and in the next video I'm going to show you something called error approximation.